Hello guys, welcome back to my channel, Maison African Motives, still working on power machines N5. In this platform we shall be focusing actually on the question paper which was written in July 2022, that is for power machines N5. So we shall just quickly rush through the question paper and see what we had, guys, as we know your instructions and everything you'll be given so that you must be able to answer properly the question paper that should be given. So I'm not going to waste much of your time. We shall just quickly rush through the questions that we had. On the first part, we are given a question 1.1 to draw and label the graph of pressure versus volume to illustrate polytropic expansion. Okay, a polytropic expansion. So remember that a polytropic expansion is one that is written in this format of PV to the exponent of n, which is equal to c. So now the question is for us to draw a diagram to represent this polytropic. So okay, remember our pressure, guys, versus volume. All right, so that's our pressure, and here on the horizontal axis, that's your pressure, that's your volume. All right, so the horizontal axis, that's your volume. So that's your pressure here. Let's just write pressure in kilopascals. Okay, and this is our volume here. All right, which is in cubic meters actually. All right, so that's your volume. So polytropic, you shall have something of this nature. All right, so that is your polytropic. PV to the exponent of n is equal to c. So at this point you'll be having 0 for both volume and pressure. So that is what actually we just needed, a simple illustration, just a simple illustration. All right, so now we are given on 1.2 to state the second law of thermodynamics. Okay, so without wasting much of your time, guys, thermodynamics, we know that it states that heat flows spontaneously from a substance of higher temperature to a substance of lower temperature, and does not flow spontaneously in the reverse direction, that is from the lower to the higher. It doesn't do that. Okay, but it flows from higher to a lower temperature. That is what we have got on the second law of thermodynamics. So I think it's actually fine with the part that we are given in this platform. All right. Oh, so sorry for that. Okay, sorry for that, guys. Okay, let's see this part now. We are given that various options are given as possible. Answer the following questions, choose the answer, and write only the letter A to D next to the question number 1.41 up to 1.43 in the answer book. Atmospheric air contains approximately and by volume. Okay, so what do we have when we are referring to atmospheric air? According to volume. Okay, so remember, according to volume, we shall have nitrogen having 79% and oxygen has 21%. This is according to volume. So in this case our answer is going to be A. All right, so that's our answer there, which is going to be A. All right, let's see another part. What are we given? So if it was the by mass, okay, by mass, that is where we have the opposite 77% here. Okay, that's one. That's by what? By mass, which is the B. This one, it's by mass. Okay, by volume is the first one. All right. All right, on 1.4 you're given the saturation temperature of steam at 2500 kilopascal is. Okay, so all you need is to have your steam tables. Remember from your steam tables, guys. Okay, so what you do, you have to mark the pressure that corresponds to 2500. Okay, so in this case we have got our 2500 on this page here. All right, here, that is where we have got our 2500 here. All right, so I think we see it the 2500. So I'm just going to just draw a line so that we can just see properly here at 2500. This is it. All right, so from this part here, this is your saturation temperature, TS, okay, in what, in degrees Celsius. So as you can see, at 2500 our temperature is 223.9 degrees Celsius. So this is what we need here, 223.9, the temperature at what, at 2500. That is the temperature corresponding. This one is the one that you're going to write, so which is this one, and on A. Okay, so our answer is going to be A. Okay, so that's what we had in 1.42. Okay, we move on to 1.43, which is stating that governance may be broadly be classified as. So how do we classify governance, guys? Okay, so governance, these are actually centrifugal and initial, which is on A. So this one is an A. That's what we had. So that's what we had, guys, on question number 1, which is actually just to work out. I think, guys, this was just direct. Okay, so let's quickly move on question number 2 now, where we are given on thermodynamics of gases, where we have got a gas which is at 22 degrees Celsius is compressed. Take note, the gas is compressed isothermally. Okay, so let us just list our information, guys. This is an isothermal part, and it's a compression. Okay, so the first thing, when you are dealing with isothermal, it means T1 is equal to T2, that is in isothermal. Then this one, it's a compression, so we shall see the effects of us having a compression, because remember, it can be expansion or it can be compression, but this one is a compressed, so it can be expansion, so it's going to affect us in the calculations later on. Okay, so the temperature, that is the initial temperature, which is T1. Okay, but we say T1 and T2 are the same, so T1 in this case is given as 22 degrees Celsius. So all you need is to add 273 so that it can be in Kelvins. Okay, that's 295 Kelvin. So that's what you're going to have. But remember, this is isothermal and the two are the same. That means T2 is also equivalent to 295 Kelvin. That's our T2. All right, so that's what we had. And also, and a volume of, that is from a pressure and volume, that is the initial again. So you're given the initial volume, which is 4,2 cubic meters, sorry, and the volume ratio of original to final, that is V1 to V2. So the volume ratio is V1 as to V2, which is 3:1, the one that we are given here, 3:1, this one. Or you can write this as V1 over V2 is equal to 3/1, which means we can play around this to find V2. Okay, then that's what we had. And R is 0. That is the gas constant. The gas constant is 0.288 kilojoules per kg Kelvin. So that's what we had in this case. So we are not going to waste much time. This is the information. Let us quickly run through the first question. 2.1 is to calculate the volume after compression. Remember, it's compression. Okay, after compression, what is the volume after compression? That is our V2. So this one, it was not a matter of fact, because remember, we are given the ratio between V1 and V2, and we are given V1. So we are just going to play around our formulas. That is 2.1. Okay, so in this case, remember, we said V1 over V2 is equal to what? 3/1 from our ratio here. So since we want V2, we can make it to be the subject. You can cross multiply and make V2 to be the subject. So if we cross multiply here, that's V1 is equal to 3 times V2. That's 3V2. We can divide by 3 both sides. So that means our V2 in this case is going to be V1 over 3. And where is our V1? We have from the information, our V1 is 4,2. So that's 4,2 cubic meters over 3. and that will be the value of V2, which is 1,4. So it's 1,4 cubic meters. So this is our V2. So we just need this information because you never know, later on we might need this. So V2, we obtained it as 1,4 cubic meters. I'm just listing down, maybe we might need this later on to use it. Okay, so you never know what is going to happen, so just leave it like that. Okay, so that's it. Let's see the 2.2, where we are given in this case to find the pressure upon completion of the isothermal process. That is the pressure upon completion. That is the second pressure, which is P2. So all you need, guys, is to work out with your formula sheet and so forth. So there are so many things that you have, guys, from your formula sheet. Remember, we can actually apply this here. P1 over P1 V1 is equal to P2 V2. Okay, it's an easier thing because we have got all these. So all you need is to check here. You have your information. Okay, what we need, do we have P1, do we have P2? Okay, so that's what you're supposed to ask yourself. Do we have P1, guys? Let's see. Okay, from a pressure, looks like we skipped something here because like it can't be missing everything. This one, P1, we missed the P1 here, 120 kilopascal. So which means we can actually win if we use this formula here. We are going to win this one. We are going to win. Okay, so take note, we do not have it. If we had a process like the one that we had, the polytropic, we're going to use this one with an exponent of n, but this one we are not using because we do not have, we use it when we are given that formula of this nature. Okay, so this one is not going to be applicable. We use this one on 15. Okay, so that's 2.2. so P1 V1 is equal to P2 V2. What do we need? We need the pressure after completion. So all you need is to divide by V2 both sides. So it means P2 will be equal to what? If we divide by V2 both sides, that's P1 V1 over V2. We have made P2 to be the subject, which is the pressure after completion or after compression. So all we need, guys, is our information P1 and V1. That's 120 and 4,2. So we've got 120 times 4,2, everything over V2. Remember, we calculated V2. That's why I said we have to write this information. V2 is now 1,4. We calculated this. So we are going to obtain pressure here, which is 360. Pressure is in what? Kilopascals. That's what you need to know. Pressure in kilopascal. So that's our pressure, guys. That's our P2. So like we do not know that we might need to use this, so let's just write it aside also. P2, we obtain 360 kilopascal. You might need to use those later on. We do not know. Okay, anyways, let's see another part, which is on 2.3 this time. Okay, the mass of the gas. Okay, so where are we going to have the mass of the given gas? All right, so it's a matter of play around with formulas, which one is going to be best and so forth, but very much concerned with this formula here. Let us try to have something from our PV is equal to MRT. All right, we know that all right, PV is equal to MRT because we've got everything there. So if we are to use this, if you are to use 2, you're going to write P2. Okay, here it will be P2 V2 T2. If you use the first one, it is going to be P1 V1 T1. Okay, so take note about what you're going to write. Okay, like I said, it can be P2 V2 is equal to MRT2 like this. Okay, so still it's one and the same thing, provided you are using these values as they are. So I'm going to use this one. Just make M, since we want the what? The mass. In this case, we want the mass of the gas. So I'm just going to make M, which is the mass, to be the subject. So divide by what? By RT1 by RT1 here. So that's gonna cancel. and we are left with M. So our M, which is the mass, that's P1 V1 over RT1. So we can easily substitute the information that we are given. In this case, that's your P1, which is 120 kilopascal. Just substitute as it is. The V1, that is 4,2. All right, everything over R times T, which is the R there, we are given 0.288 times T1, which is the temperature in kelvins, which is 295. Remember, we added this so that it can be 295. It's not like we had something like this previously, no. So all you can do, guys, using your calculator properly, you're going to obtain something like 5,932203, something like that. So if you round off to 3 decimal place, it will be 32. Okay, so this is our mass in kgs. All right, so that's what you simply do or work out. So which was the same thing. If you are to use this side, you are going to obtain the same thing. So let's just write this down. We might need also to use this. That's our mass, 5.932 kgs. All right, let's move on to the other question, which is in this case on 2.4. The work done during compression in kilojoules. Okay, so that is where now we are going to see the effect of this compression. When it is being compressed, it means the work done is going to be a negative there, because it's what? It's compressed. It's a compression. Okay, in expansion it's a positive, but this time it will be a negative value. All right, what is the formula for work done, by the way? Okay, this is, guys, again, you and your formula sheet in this case to find your work done. So work done, there are so many formulas that you can actually use. Okay, but here we're just going to work out on this one, but you can actually use MRT. Do we have it here? Do we have it here? All right, it's not. Let me just write it down. Okay, I said we can use this. Okay, and the other one is not written, so let me just write it down. So this is 2.4, remember. All right, so our work done is going to be equivalent to, if you use this one with n-1, that is for polytropic and so forth. So here we are not using this one. We do not have the index with this one. Does not even apply in isothermal, okay, or even in isobaric, it doesn't apply. Okay, so this is the one that you're going to use. The work done, P1 V1 ln V2 over V1. All right, so this can also be given as this formula. You can write it as the work done is equivalent to MRT1 ln, it will be P1 over P2. So you can actually take this also. Okay, anyways, let's just write this one. So P1 V1, that's our information. Now all you need is to substitute your information properly. P1 V1, that's 120 times 4,2. 120 times 4,2 ln V2 over V1, that's V2. Remember V2, we calculated this and obtained 1,4. So it's 1,4 over V1, and our V1 is 4,2. So that's where our negative is going to be obtained from, because this is a smaller value. It's a fractional. It's a fraction that you're obtaining, so it's going to be negative. So that's how a compression works like. Okay, so anyways, guys, all you need is to simplify properly from your calculator, and you're going to obtain negative 553,7005, something like that, 0059, which is going to be 0.1. Let's just 0.1 like that in kilojoules. Remember, work done is measured in what? In kilojoules. All the units, the pressure was in kilopascal, so definitely your work done is going to be in kilojoules. So like I said, the negative here is the one that is indicating what? The compression. It's because of what? We are under compression. That is why we are seeing our work done being a negative like that. All right, so that's our work done, guys. Let's see the other part that we had on 2.5 now, which is the amount of heat absorbed or rejected in kilojoules. What is the amount of heat that was being absorbed or rejected. When you are talking of the amount of heat, that is your Q. And remember that, let's just write it down here. Remember that Q is equivalent to the sum of what? The work done plus the change in internal energy. Okay. But since we know that the change in internal energy is equal to MC change in T, and we said T1 and T2, they are the same. So which means this one is going to be S0, this one. So which means the change in internal energy is what? It's S0, this one. Okay. So if it is S0, that means our Q, which is the heat, is going to be equivalent to the work done, because this one is going to be S0. Okay. So that's your work done as it is, and our work done was minus 553,701. Yeah, our work done, this one that we calculated here. So that is going to be our Q in this case. Okay, because the change in internal energy, that is what? That is S0 there. So as you can see, it's a matter of playing around with that, with the formulas that you are given there. It's a matter of playing around with the formulas and so forth. Okay, let's see. On 2.5, we are given to calculate now the change in entropy in kilojoules. Okay, the change in entropy in kilojoules. Okay, so what is our change in entropy? So the change in entropy is given by this formula here. Here we've got change in entropy here. So actually we can just write anyhow. Okay, let me just write it down, and it's M CV, that is with the constant volume. Okay, the specific heat capacity on constant volume R ln V2 over V1, like that. Okay, so that's what you're going to have in this case, but we are not going to like waste much time here, because remember T2 over T1 are the same. Remember T1 is equal to T2, so which means if you divide, you're going to obtain 1, and we know that ln 1 is equal to what? Is equal to 0 from your mathematics. So this part is going to give us a 0 here, so which means our change in entropy is going to be M times this now. So it's going to be MR ln V2 over V1, because this one is actually giving us what? S0. So that's our final value now. The change in entropy, that's mass. Okay guys, let us just take our information. The mass, we have got the mass here 5.93, 5.932 times R, which is your R in this case 0.288 times ln V2 over V1, that's V2. Remember V2 is 1,4. Okay, so that's 1,4 over V1, which is 4,2. All right, so just like what happened, because of compression, it's going to be a negative again. Our change in entropy is going to be a negative, so this is negative 1,87688, something like that. So it's going to change into 7, yeah, which is kilojoules per kg. Okay, so in this case we are given the units just kilojoules. Okay, just kilojoules in kilojoules. So that's what you're going to have for the change in entropy. Okay, but it's supposed to be like per Kelvin. That's what we had. So I don't know guys, but as you can see, that's 20 marks, and I don't know, according to you, does it correspond the number of marks and the working and the calculations? Anyways, let's see, let's discuss on the comment section. Let me know what you think about this. Okay, anyways, let's move on to the other part of the question, where we are given on question 3, a fig in fig 1 below shows the feed water enters an economizer. All right, so we've got feed water entering the economizer, leaves at this temperature. So this is the initial temperature, that's your T1 here, 26.7 degrees Celsius, which is this one, T2. Okay, so the exit pressure is 92% dry, which is 0.92 as a decimal. If you divide by 1, and this is this one. Okay, so the steam leaves the superheater. This is the superheater at 1500 kilopascal. Okay, this is the one that we have got here written as 1.5 mega. So our pressure is supposed to be like in kilopascal, so that we can use. So this 1.5 megapascals is 1500 kilopascals, which is the same as this one also, which is 1500 kilopascals. So P3 is equal to what? P4. Okay, this is what you're supposed to know. P3 will be equal to P4. Okay, then we are also given here the mass of steam. Okay, let's just write this and we can answer the question. Let's just put our information down. So we've got the mass of steam, which is, in this case, the mass of steam is 2500 kilogram per hour. Okay, so that's 2500 kgs per hour. Okay, the mass of coal, this is the fuel. Coal is the fuel. Okay, so this is the mass of the fuel, which is 200 kgs per hour. Okay, so we've got the mass of coal, which is the fuel. Okay, that is your coal in this case, and this is ms for steam. This is your steam here. All right, then you're given the calorific value is 35 megajoules per kg. That is our calorific value. This is 35 megajoules per kg, but as you can see, our units, guys, they are being in kilopascal, kilo. So we are supposed to write also this in kilo. So how do we convert 35 mega to kilo? This is like what we just said there. 35 mega means to the exponent of 6, and as we need kilo, so kilo is to the exponent of 3. So which means you are going to separate this exponent of 6 into 10 to the exponent of 3, 10 to the exponent of 3, where this one means kilo. Okay, so that is what you're going to have. So that is like 35 kilo. So this 1000 now you multiply to the 35. So it's 35 times 1000, which is 35,000 kilo. Okay, so it's like times 10 to the exponent of 3. So this and this multiplies, so we're left with 35,000 kilo. All right, so that's 35,000, okay, kilojoules per kg. So this must be in kilojoules, not megajoules. Okay, so these are some of the things that you must be very careful with when you're answering. Anyways, let us attempt our question. The first is copy and complete the diagram in question. So here I'm not going to copy, I'm just going to complete, but you are supposed to copy this and complete. Okay, so here I'm not going to copy anything, I'm just going to complete. So what are you supposed to complete? The missing values, definitely. These are the ones that you're supposed to complete. We are talking of what? H1, H2, P3 already we have completed this, and H4. So this is the economizer. So your H1, that is your entropy, that is your HF at what? 26.7 degrees Celsius. So all you need is your steam table. You go to the what? To the temperature. Suppose you are given temperature and you find HF at that temperature. Okay, that is your HF. So let us go at 26. So 26, let me just have the page somewhere here on this page here. 26.7. okay, this is, where did I put this? But I think it can be clear if I just put even a ruler like this. Okay, that's 26.7 here. So as you can see, at 26.7, okay, that is your HF. You want HF, this one. Okay, so your HF here is what? 112, this one, at 26.7 degrees Celsius, which is your temperature. Okay, you need the corresponding what? The corresponding HF, this one. Okay, the corresponding HF, which is this one. This is your HF, which is 112. Okay, so that's 112 there. That is what you simply need in this case. Okay, so this is 112 kilojoule per kg, and also the units, they will be written here, kilojoule per kg on top there. Okay, so this is 112 kilojoule per kg. Okay, H2 is the same at 47,7. So at 47,7 here, this is your 47,7, your HF. Okay, this is your HF here, which is 200. So it corresponds with 200. So that's 200 kilojoule per kg. Okay, X, everything is here. Then this H4 is the superheated steam, so it's like H soup, which is the superheated steam, and this is your superheated temperature. So you go at 1500 and 200 on your superheated steam table. Okay, this is your superheated steam table, this one, which is this one. Okay, so that is the one that I'm working, or you work with this one, the superheated steam. So you have to correspond these two, the temperature and the pressure at 1500. Okay, so let's do this, guys. This is here. All right, like this. This is my pressure here, so you take note here from your pressure here. Okay, this is your pressure here of 1500, and versus the what, the temperature. This is a temperature of 200. So where these two meet here, they meet at this point here at the superheated steam is the one, the H soup. This one is the one that you're going to take there, which is 2796. This one, that's your superheated steam at 1500 versus 200 Okay, so that's 27, that's your H4, which is your superheated steam, which is 27, we said 2796. Okay, that's kilojoule per kg. Also take note, guys, you take this one on both, they must work together. Where they meet at superheated steam, that is your answer. Okay, so that's how you simply take this. So you've completed your diagram just like that. It's all about the steam table. So H1 is there, H2, P3, and H4. Remember I said P3 and P4 are the same. So here you write it in kilopascals. These two, they are the same. Okay. Then 3.2, calculate the mass of steam per kg fuel. Okay, so this is direct, guys. Mass of steam per kg fuel, which means we simply need ms. Oh, I'm throwing this away, guys, of which is the one that we want, that we must use. This one, mass of steam per kg fuel. So it's mass of steam over mass of what, fuel. That is what they simply mean. Okay, mass of steam over mass of fuel. So this is 3.2. okay, so that's mass of steam, which is 2500 here, 2500 kilogram, which is a kg, 2500, sorry, over the mass of fuel, which is 200 in this case. Okay, so that's what you're going to have in this case, and it's going to give us something like 12,5. okay, so that is your kg steam per kg fuel. Okay, per kg fuel, that is what they mean. 12,5 kg steam per kg what, per kg fuel. So all you needed is the formulas and so forth. I think it's something that can be easier to work with. Okay, let's see 3.3. Calculate the heat transfer to the economizer. Okay, this is the economizer here. So for you to have the heat that was transferred to the economizer, you need the mass, this one, the mass of steam over mass of fuel times the enthalpy, but you are going to subtract this one because this is the economizer. So it's H2 minus H1. Okay, just you subtract these two. Okay, so this is the formula 3.3. so we said heat, so you can just write this as Q. Okay, so Q is equals to, it's supposed to be like this, mass of steam over mass of fuel. Then since it is the economizer, you subtract these two, and which are affecting the economizer. So economizer is affected by H2 and what, H1. So you subtract H2 minus H1, just like that. Okay, So this one we have already calculated this. We got 12,5 ms over mf is 2,5. 12,5 times, you simply need H2 minus A. So you see, if these values are wrong, which means everything is going to be wrong. So you subtract 200 minus 112. So it's 200 minus 112, like that. So that is your Q, which is, in this case, I obtained something like 1100. That's kilojoules per kg. So that is what you are going to have in the economizer. All right. Okay, just like that, guys. I think it's very, very simple. The economizer. Then we need, in this case, 3.4, the specific heat, the specific enthalpy of wet steam, which is H3. So here we've got H3, which is H wet, and the heat transferred to the evaporator. So just like what we calculated to the economizer, we are supposed to have this as H3 minus H2, but since we do not have H3, that is why they have to ask us to calculate this H3. So it's just one formula, but you have to know that heat transferred to the evaporator, this is evaporator, is guided by H3 and H2, so you just find the difference. Sorry, the same with the superheater, H soup, which is H4 minus H3, just like that. Okay, so H3 is needed and this is H wet. Okay, where, guys, you know that H wet is equivalent to HF plus X HFG, okay, which is our H3. So this is your H3, which is H wet. So HFG, these you find them at this pressure because you are given the pressure. Remember, you are given the dry, the constant, that is the evaporate from our dry constant, that is the one that you are given of steam, so which is 0.92. So this one, there's nothing that you're going to do, you already have it. All you need is to find HF and HFG from what? From 1500 kilopascal. So from your steam table, again, let's go back to our steam table, guys. 1500. All right. So this one, you're using the normal one, not the superheated, but the normal one. Okay, what we need, HF. So this is at what? 1500 kilopascal. Okay, what is our HF? Okay, this is 1500 here. 1500. Okay, 1500 here. All right, something like this. All right, that's your 1500 there. So at 1500, guys, what's our HF? This is 1500 and our HF here is 845. Okay, so this is 845 kilojoule per kg. What is our HFG? Okay, at the same value, HFG straight here is 1945 here, 1945. Okay, that is kilojoule per kg. So these are the values that you needed. All HF, substitute 845 plus X. Our X is there from the diagram here. That's our X, 0.92. Okay, that's 0.92 HFG, which is 1945. All right, so that's all we needed, guys, which ended up giving us something like 2634,4, okay, 4, something like that, which is kilojoule per kg. All right, so I think just like that we are done, guys. Okay, but we had also to calculate what the heat that was transferred to the evaporator. Okay, just like the economizer, we subtracted H2 minus H1, so this one is H3 minus H. That is the concept, guys, throughout. So that is our Q evaporator. So it's mass of steam over mass of fuel into H3 minus what? H2. Okay, so this one, we calculated this before. That is the one that we obtained, 12,5. So we are not going to repeat on recalculating because we already calculated this, guys. Okay, so that's 12,5 times H3. Already this is your H3, already found your H3 here. So it's 2634,4 minus H2 from your diagram. Now H2, this is your H2, which is 200. So that's 200. Simply like that, you can have your evaporated that is the heat, that is 30430 kilojoules per kg. All right, that's what we have there. So I think it was a little bit direct, I don't know, according to what you said and so forth, but that's what you actually had and what you needed there. Okay, we move on to 3.5. Okay, we said this H3 is what, 2634,4. We are going to need this kilojoule per kg. All right, we are going to need this. Okay, anyways, 3.5, calculate the heat transferred to the superheater, just like the evaporator. So the superheater has got H4, it's guided by H3 and H4, so you subtract the two, just like that. Okay, the other part remains the same. Which other part am I talking about? That is ms over mf times, now it's H sup minus what, H3. That is the case, which is our H sup is what, H4. That is your H4. So it's H4 minus H3, just like that. And this was 12,5 H sup, which is our H4. Remember, we got this before. This one, we got this before, which was 2796 minus H3, which is the one that we just calculated now. This one, which is now 2634,4, just like that. All right. So using our calculators properly, this is going to be 2020 kilojoules per kg. All right, so that's what we are going to have in the evaporator. So it's very, very important that you understand how to use the formulas and so forth and everything. Okay, anyways, let's move on to the efficiency of the plant. Okay, so the efficiency, guys, as we know, this one, you are going to, that is where you now apply your calorific value. So it will be efficiency is equivalent to the mass of steam. Still having the mass of steam, but this one you take H sup, which is H4 minus H1. So remember, this is H sup over the mass of fuel. So mass of steam over mass of fuel. This time you multiply by the calorific value times 100% efficiency. Remember, it's efficiency, this one. Okay, so I think everything we have got. So this part here is the one, remember, it's 12,5, so you can write it as 12,5 over 1, because this will be like, we need the FF in the, or you just leave it like that, because you know this over this is 12,5. Okay, times H4 minus H1. This time you subtract the last one and the first one, the last one and the first one, these two enthalpies. Okay, so it's 2796 minus the first one, which is 112. Everything over just like this. We said you can write it 1 no matter what. Then take note here on the calorific value. Remember, I told you it must be in kilojoules, not megajoules. So here we converted this to kilojoules, this one, which is 35,000. So it's 35,000 times 100%. That is where everything might go wrong on this value. It must be in what? Kilojoules. So that's what you're going to have in this case, and this is going to give us something like 95,8571 and so forth, which is 857. So it's going to be 857%, something like that. So that's what you're going to have as your efficiency. Okay, then we have the last part, which is to calculate the equivalent evaporation from and at 100 degrees Celsius. Okay, so this we are actually given, remember, on our formula sheet. It's actually there. So our equivalent evaporation is equivalent to that's ms h3 minus h1 over mf into that's times 257. Okay, here guys, so it's actually like H2, because when you're dealing with H2 it will be like you are working with what, only the boiler. Okay, but here we have to consider H3, so that's what you're going to have on your formula in this case. Okay, so that's the same thing here, 12,5. Remember, mass of steam over mass of fuel times H3. What was our H3? Our H3, guys, from our diagram, that's 2634,4 minus H1. Okay, our H1, which is 112. So that's 112 everything over 1 times 2257. So guys, power machines is all about formulas. That's power machines, guys. Never worry about this subject. All you need is to revise your formulas as much as you can, and to revise as much question papers also. All right, so this is 13.9698, so it's going to affect this. That's a 0 here, then 7 here, so it's 13,970. that is 13,97, just like that. All right, which is kilojoule per kg fuel. Okay, so that's what you're going to have at 100 degrees Celsius. So it's actually always they'll ask this question to say at 100 degrees Celsius, and that's what we had in this case. So that was actually question 3, and all you needed is to apply this properly. And as you can see, guys, it's actually 20 marks. Each and every question that you are having is just carrying 20 marks, and it's supposed to be very, very clear, because if you do not know anything there, it can now become a greater challenge to attempt the questions. Okay, anyways, we are given on question 4, where we have got in this case a 100 kg, that's a 100 kg steam with a dryness fraction of 0.7 enters a surface condenser per hour. The pressure is 10 kilopascal. The mass of cooling water is 1850 kilograms per hour. The inlet pressure 22 degrees Celsius. The condenser temperature and the air pump suction temperature is each okay, then use 4,187 for what, for CP, for water. Then calculate the final water temperature. What is the final water temperature in this case? Okay, so this is actually what we have got in this case. Maybe we can just list down our information. We have got this steam here, mass of steam. Okay, that's 4.1 mass of steam here, which is 100 kg steam. Okay, that's 100 kg steam, and X, which is the dryness fraction of 0.75. okay, 0.7, and it enters a condenser air per hour. So this is like mass of steam per hour. So this is mass of steam per hour. The pressure is 10 kilopascal, so that is the pressure that we have at that point, which is 10. We shall see where we are going to apply this later on. And the inlet temperature, okay, the mass of cooling water. Now we are talking of the water that is cooling. So we have got steam here and the cooling water, which has got a mass of 1850. The mass of cooling water, 1850 kilograms per hour. So it's kg per hour. All right, then, and the inlet temperature, which is 22 degrees Celsius. So that is the inlet to the system, that is Tn. So Tn is equivalent to 22 degrees Celsius. Okay, the condensate temperature and the air pump suction temperature is 43,H, which means they are the same, the condensate and the air suction pump. Okay, so these ones, they just have the same temperature. The condensate suction, which is 43 1.8 degrees Celsius, and I think that's what we have in this case. Do we have anything that we left out? We do not have. So the question now is to calculate the final water temperature, which is T2, which is T out actually. So remember, this is Tn to water and we need T out. So where are we going to have this given the specific heat capacity of water according to constant pressure in this case, which is 4,187 kilojoule per kg. What are we going to use? Which information are we going to relate to in order to answer this question? Okay, so actually what is important is that we are going to work with enthalpy. That is in this case, remember we are talking of steam, okay, and we are also talking of what? Of water. So the cooling water and the steam, they must have something in common. And what is it that is going to be in common? It is the heat. So here the steam is going to emit the heat and the cooling water is going to absorb the heat. So we can say Q emitted is equal to Q absorbed. All right, so what is emitting is the steam. What is absorbing is the cooling water. Okay, it is the one that is absorbing the heat. This one is emitting, releasing the heat. So we know that the heat for the steam, we are going to have the mass of steam into the enthalpies, which are the 2Hs plus Hc for the condensate and for the steam. Okay, then for the water, what is going to the enthalpy, that is the heat. What is going to be the heat? That is the mass of water, specific heat capacity of water, okay, times, in this case we need the change in temperature, which is the one that consists of what? T out, which is T2, and T in. So I don't know how I'm going to write it, but let me just write it as change in temperature like this. Okay, but you must know that this change in temperature is the one that is equivalent to T2 minus T1, that is T out minus T in. Okay, so let us calculate this. Since we have got T in, then we can be able to calculate T2 later on. So let us focus on calculating the change in temperature. So we are going to focus on this, then later on we calculate the exact part that we need. Okay, I think that can be easier that way. I think that can be much easier. So in order for us to calculate these guys, that means a lot actually. Okay, let's see. Let's make our change in temperature to be the subject. So definitely divide by mass of water, specific heat capacity of water. Here the same thing, mass of water, specific heat capacity. So that will be your change in temperature, which is going to be ms into Hs plus Hc over mass of water, specific heat capacity of water. Okay, so on our information, this one is the mass of steam, that is mass of water is there. This is your mass of water here. Okay, these two are there, this is there, but we do not have Hs and Hc. Okay, so Hs, that is the enthalpy for steam. Okay, then Hc for the condensate. Okay, so which means we have to find Hs here, and also we have to find Hc for the condensate. Okay, so what is our Hs? What are we going to? This is for the steam, so is the dryness fraction times Hfg. Okay, that is the enthalpy that you are going to have as for steam. Okay, where are we having our x is there? That is our dryness fraction of 0.75 times Hfg, which is at this pressure, because we are given for steam the pressure is there, which is 10 kilopascal. So at 10 kilopascal, what is your HFG? Okay, so that is what you're asking your question now. At this 10 kilopascal, at 10 kilopascal, what is your HFG? So all you need is your formula, your steam booklet, guys. At 10 kilopascal, remember I told you the pressure, you go under the pressure versus what, versus the steam. Okay, so that's what you're going to simply need. So here, guys, this is our 10 kilopascal here, and that's our HFG here, which is 2393. So you take the one that corresponds at what, at 10. So I don't know, but let me just put it this way. That is at 10 here. All right, something like, so my HFG, this one is at this 2393, this one. Okay, so that is the one that you're going to take, which is 2393 kilojoule per kg. All right, so if I'm to multiply this, I'm now having the entropy for what, for steam, which is 1794,75, something like that. Okay, so this is what I'm going to obtain in this case, kilojoule per kg. Then I move on to the condensate, which the two, they are at the same temperature. Okay, the condensate, and that is it. I want us to have this. Okay, let's just write the formula first, which is let's come back to our condensate, guys, which means, what do we have here? Remember, we have got our specific heat capacity for water, which is going to affect our condensate, and the temperature, that is in this case, you remember we are told that these ones, they are operating at the same temperature, which is TC, which is 43.8 degrees Celsius. So we need this for the condensate also, and this, and also what is going to miss. Okay, let me just write it down. CP into that's TS minus TC. All right, so this is the formula that you're going to take for the condensate, which is CP, that is the specific heat capacity for the water, guys, remember. So this is, let's just put W for the water here, and the TS we do not have. This is the steam temperature, because they are at the same part. So you're going to use at 10 kilo, what was our temperature? Okay, at 10 kilopascal, this was your temperature. This is your TS. The temperature is what, 45.8. this is your at 10, 45.8 degrees Celsius. So this is the temperature that you're going to take at 10. You're still at 10, which is 45. So let's just substitute, guys. This is 4,187. Okay, we're having a lot of things now. 187 into TS. All right, that's our TS now, the one that I just say, this one. So this is your TS. Okay, TS at 10, which is 45.8 from your steam table. That's 45.8 minus TC. This one, we have our TC here, which is 43.8 from the condensate that we have. So at the end, all you need is to evaluate properly from your calculator, and that will be something like 8.374 kilojoule per kg. Okay, so the way I actually did here is to separate these two, so that it can be easier for us now to substitute these two now into the formula, because remember, this is not what we need. What we need is the final temperature, and we said we are going to take this now here. Okay, this is what we needed, HC and HS, so that we can have our change in temperature, which is going to give us our T2. So the change in temperature is not the answer, but it's going to help us now to find what we need. So let us just put in our values, guys, from this formula that we had. We are now at change in temperature, which is MS. So it's a matter of substitution, guys. Remember, your ms, it was 100 here, that was 100, so it's now a matter of substitution. So that's ms, which is 100 times hs plus hc, which is the ones that we obtained here. Hs, okay, sorry, that's hs plus hc, so we have to combine these two together. Okay, so that's hs, which is 1794.75 plus hc for the condensate, which is 8,374. all right, so you're simply adding these two. Okay, so that's what you're going to have, everything over what, let's get to our formula. Okay, everything over the mass of water times the specific heat capacity of water. So it's the mass of water. Where do we have this? Okay, this is your mass of water here, 1850. Okay, so we've got 1850 here times Cp for water, which is 4,187. We also have this. Okay, 4,187, this value. So it's 4,187. So all you need, guys, is to use your calculator properly, calculate your change in temperature. So our change in temperature is going to give us something like 23,278 degrees Celsius if you calculate properly. But I say this is not our answer, because remember the question is asking us to calculate the final water temperature, the final water temperature. So the final water temperature now, since change in temperature is T2 minus T1, that means T2 is change in temperature plus T1, that is your T2. So your T2 is going to be this change in temperature, 23,278 plus T1. Okay, our T1 is the T in, that is the T in. Our T in is 22 here. That's your T1, which is T in 22. So if we add these two, we are going to obtain something like 45,278 degrees Celsius. So this is your T out. Okay, so that's what you only needed, guys. So as we are moving, actually we shall have to answer this question, or to approach this question in another way. So that is what we are actually going to do. So as time moves on, guys, I shall actually come back again with a similar question, but working it the other way, not exactly the way like we did this one, but we can actually refer it in another way, but so that we can understand these ways, because someone might not understand what is actually happening here, but I hope it is going to be clear. Okay, on 4.2 we are given that there is a gaseous fuel that has the following volumetric analysis. Okay, so this is actually a volumetric analysis that we are given, and this is for a what? For a 1 cubic meter. So which means the volume here is 1 cubic meter of what? Of fuel. Okay, anyways, that's what you have. And determine the balanced chemical equation of the combustion reaction of each, that is CH4, H2, and carbon monoxide, that is methane, hydrogen, and carbon monoxide. Okay, so these ones are the balanced. So it's like you are coming direct from your what? Each, you are working each, you are balancing each. That is what is happening. So how can we balance CH4? Okay, from our formula sheet, we have got this formula for for carbon. When you are working with the hydrocarbons, you can actually work out from this formula. Let me write it down. So because here we are given methane, so we can actually work with hydrocarbons here. So this is 4.2. All right, that's 4.2. Okay, so it's now 4.21. okay, so like for CH4 we are going to have CXHY, okay, plus, so just write down that formula that I showed you as it is. That's y over 4 O2, okay, which is equal to x CO2 plus Y over 2 H2O. Okay, so this is our formula, and all we need is to substitute. Remember, this is CH4, so which means X is 1, X is equal to 1, Y is equal to 4. So that's where we can balance our methane, which is CH4. So CH4, this is just substituting X1, just repeating, okay, plus X, which is 1, so it's 1 plus Y here, that is 4 over 4 times O2, which is equal to X, which is 1, CO2, so it's just 1, like that. Okay, plus Y over 2, that's 4, so it's 4 over 2 H2O, so you just substitute the X and Y as they are. Okay, so that's CH4 plus, if you add this one, is 1 plus 1, which is 2 O2, equal to CO2 plus 2 H2O. All right, so at this stage, is this balanced, guys? How do you check it's balanced? You calculate the number of carbons. How many are they? 1 here, 1 here. Okay, how many oxygens here? 2 times 2 is 4, so there are 4 here. So here how many? We have got 2 times 2, which means they are now 2. So 2 plus these 2, they are 4. Okay, so the oxygen, they are fine, they are balanced. Let's move on to hydrogen. There are 4 here. The hydrogen, this one is 2 times 2, which is, they are also 4. So the hydrogen, so this one is balanced. So there's nothing that you're going to do, it's already balanced. The number of carbon equal to the number of carbon on the right, just like hydrogen and oxygen. Okay, so this one is balanced. How are we going to balance for H2? Okay, where are we going to have our H2? So for H2, for you to balance H2, you have to like go back to your creation of the formulas. Okay, where we know that hydrogen plus oxygen should give us water, isn't it? But is it balanced? Is it balanced? Because we need to balance for H2. So is it balanced, this one? Okay, let's calculate how many hydrogens do we have here. We have got 2. Here we've got 2, yes. But here, oxygen, here there are 2, here there's 1. So how are you going to balance? Here we have got 2 oxygen here. So here it's 1. So as you can see, if I can multiply half, 2 times half, I remain with what? With 1 oxygen. So I'm going to write this as H2 plus half O2. Not as 2 times order, but I know that there are 2, so half of 2 is 1, so they are now 1, so it's half times 2, which is 1. So we are now left with 1 oxygen here, which is the same thing here. We have got 1 oxygen. Okay, so I think that now it's now balanced. Okay, is it balanced? Now it's balanced. Here it wasn't balanced. Okay, so let's see how we could balance this again. So it's not like it's a one-sided type of equation. No, it's not a one-sided type of equation, because someone can choose this. Someone can choose this. Since here there are 2, if I am to make them 2 here, I have to multiply by 2. But take note what is going to happen. This is going to be 2H2, or like this, which means now the oxygen, they are 2, but the hydrogen, they are now 2 times 2, which is 4. So you multiply the prefix and 2, so 2 times 2 is what? 4. So that means for this to be equal here, I must have these 2 oxygen as they are, because they are already 2, because now I'm having 2 oxygen here, so this is not going to change. So I'm going to remain with 2 oxygen as they are. But the hydrogen, now they've changed, because it's now 2 times, which is 4. So how can I make these 2 to be 4? I have to multiply by what? By 2 also here. So if I multiply by 2, 2 times 2 is now 4. So I have 4 hydrogen, okay? 2 oxygen, 2 oxygen. So which means this one is balanced. So I can take this, or I can take that one. It was any of those. That is how you're supposed to answer this question, guys. Okay. Let's see another one. Okay, where's this? Which is carbon monoxide. So you need to formulate where carbon monoxide we know that carbon monoxide is an incomplete, so we have to add what? We have to add oxygen, so it can give us what? Carbon dioxide now. So this is carbon monoxide, oxygen, carbon dioxide. But is it balanced? Let's see. Our main number of carbon, it's 1 here, it's 1. Okay, oxygen here we've got 1 plus these 2, which is 3, so we have got 3 oxygen. Here we have got 2 oxygen. So how are we going to balance this? Okay, how? If we are to check here, there are 2, so if I divide this by half, I'm going to be left with 1 oxygen plus 1 oxygen to make them 2, so it can balance. So I can write this as CO plus half of these 2, so half of these 2 oxygens. I'm now left with 1 oxygen plus this 1 oxygen, they are now 2, which is equal to, this is now balanced. So this is now balanced. But was it the only way that I can do this? Okay, let's think, guys, along the lines. Okay, let's say here I multiply this by 2. Let me see. Okay, if we are to multiply this by 2 here, it's going to be like this. Okay, which means how many carbons are now there? We have got 2 carbon, then the oxygen will be 2 times 2, which means we have now 4 oxygen now. Okay, so how can we achieve 4 oxygen? Which means we have to multiply this, because already it's 2 plus 2, there will be 4, and carbon, yes, so it can balance. So it's O2 plus 2CO, like this. 2 carbon, okay, 2 oxygen plus another 2 oxygen, which is 4 of them, that is 4 oxygen. Okay, so that can make sense. So I don't know which one did you use, or there can be another one, I don't know, but what matters is that is it balanced? That is what matters. Okay, otherwise all of this does not matter at all. What matters is it what? Balanced or not. Okay, so the 4.22 is to calculate the total volume of oxygen consumed in combustion as oxygen reacts with each of the fuel. So oxygen is going to react with each of the fuel. So how are we going to have the amount of oxygen as it reacts with each? Okay, it's a very, very interesting question, and confusing at the same time if you don't play around it. So this is volume of oxygen. Okay, so the volume of oxygen, this is how we are going to do it. We are going to start, guys, from the scratch, which means we have to follow back all those calculations that we did here. Jesus, and I don't know if I wrote all of them and put this aside. You see now these things of just writing, guys. Okay, we are going to start here from our methane, from our CH4. Okay, the amount of oxygen here, according to this CH4, the amount of oxygen is 2. It is going to possess 2 portions of what? Of CH4. Are you getting the sense? So it's 2 portions of methane. So it is going to be 2 portions of what? Methane. We are going to take this, the percentage of methane, okay? Plus, we move on. We talked of oxygen and what? Water. Okay, in water, remember in water, guys, this is now okay, here is there. In water, this was it here. In water, we had half oxygen here, because we want where there is 1, so we are not going to take this one, but this one with 1 over here. So for hydrogen, which is 1 here, your oxygen was a half, so it's half of what? Hydrogen. Okay, which is half of the complete part, which is your hydrogen. It's from hydrogen, so it's half of this hydrogen. So our oxygen has got half amount of hydrogen. Okay, and the last one was which other substance, which other part that we had? It was carbon monoxide here. So in carbon monoxide here, that is in carbon monoxide here, oxygen, it's going to contain half of it, so it's half of the carbon monoxide. So you take the percentages now of these, okay, here where these are the percentages. CH4 as a, this is the percent, 32%, which is as a decimal is what? 0.32. So it's 2 times 0.32, okay, plus half of the hydrogen now, which is 0.40 as a decimal, plus in carbon monoxide is 20%, so half of it, so it's half of 0.02, 0.2 guys, as a, okay, that's 0.2, okay. Oh, so that's what we actually needed there. So that's 0.64 plus 0.2 plus 0.1, okay, then we can add, which is going to give us 0.94, yeah, something like this, which is cubic meters, and this is oxygen, is volume of oxygen per cubic meter fuel. All right, so that's how you calculate the volume of oxygen. You have to revisit each and every part that you calculated. You take the amount of oxygen in each and every part that you calculated before. I think by that it can actually make sense. All right, then the volume of air together with the volume of products of combustion. So this is volume of air and together with the products of combustion. Take note. Okay, so let's start with the volume of air. So this is by volume, guys, and if you cross-checked on our first question, we said by air, by volume, I mean it is going to be 21 versus what, 79. So which means air is going to take out of 21% of oxygen, which means air is going to be having the 100%. So it's like this, 4.23. We have got 21% of oxygen by volume. So which means air is at what? At 100%. So 100% over 21 times definitely the volume of what? Of oxygen. This is going to be the volume of what? Of air. Okay. So that is our volume of air, which is 100 over 21 times the volume of oxygen. Okay, and we calculated this before. This is the one that we just got, guys, and it was 0.94, the one that we just calculated now this one, which is the volume of oxygen, this one. Okay, so by doing this, guys, I don't know which decimal you're going to obtain, but it's going to be 4.4619 and so forth. So it's going to be 76. Okay, that's cubic meters air per cubic meter fuel. Okay, so that's what you just needed, just like that, guys. You have attempted this, but it wasn't this only, it was and together with the volume of the products of combustion. So we need also the products of combustion. And which are these products of combustion? Okay, and how are we going to calculate their volume? Okay, so I don't know if I'm going to put it in a nicer or easier way. I'm looking for this ruler now. All right, sorry guys for that. I want to put it in a table, so that's why I'm looking for this thing here. So like I said, I don't know if it is going to be clear actually, but I just need two things actually here. Yeah, let me just work with these two things. Or are they two things or just two columns? These are just two columns anyway. Okay, so let me just work with this. I don't know, sorry for wasting much of your time, guys. I don't want to waste much of your time, but that is what happened actually. Okay, so these are the products, okay, of combustion. So let's just have our products here, and then the volume. All right, so we've got which products? Let's just list them. Nitrogen is one of the products, definitely. Carbon dioxide, remember from carbon monoxide and oxygen we obtained carbon dioxide, then we obtained also water. Okay, so this is what you're going to work with. So we just need these guys. Okay, so where are we going to have nitrogen? The volume of nitrogen, because we actually need the volume of nitrogen. Okay, so remember by nitrogen it consists of what? 79%. Remember oxygen, you said 21%, and nitrogen is 71%. So nitrogen is going to be 79% of what? Of the air. Okay, so it's 79% of air, plus not only that, because we also have the nitrogen here. Okay, we also have nitrogen percentage here, so we are going to add that. Okay, so that's 79% of air, which means 79 over 100 times the volume of air. So guys, because I was like mixing these things now, but I hope we still have that value here. Okay, it's here for, remember, for air, this one 4.476, guys. This is 4.476, so please just take it properly, okay, like this. So this is according to the percentage, then plus the nitrogen, that is the one that we have here. We've got a lot of things on this question, guys. Okay, this nitrogen here, which is as a decimal, it's 0.08. Okay, so that's what you're going to take, and that is going to give us 3,616, that's cubic meters nitrogen, okay, per cubic meter fuel. Okay, so that's what you're going to have in this part. We are done. We move on to carbon dioxide. Remember, we listed this down, guys. Okay, and this ruler is too small. So guys, you can do something that is presentable more than the one that I'm doing here. I'm just showing you what you're supposed to do, so you can actually do something much better than this. Okay, so let's move on to the other product. We said we have got what? Carbon dioxide. All right, so where are we going to have our carbon dioxide? Okay, our carbon dioxide, we go back to the basic reaction that we had of CH4. Okay, so let me take that. The basic one, that is this one, is the one that is going to give us everything here. So remember here, according to methane that we had, our carbon here, this is where we had our carbon dioxide as a resultant. Okay, because we need the product, which is carbon dioxide. It's only one that we have. We only have one part here of what? Of carbon dioxide. Only one out of the whole of the methane. So it is going to be like this. Okay, you take this quantity, which is 1. So it's 1 times the percentage of methane. Okay, so you're going to add, to multiply to the percentage of methane. Okay, then you add, just like nitrogen, here you are going to add the percentage of what? Of carbon monoxide, because it's part of this. So we add this percentage of carbon monoxide. Okay, so that's what you're going to have at the end. So it's 1 times the percentage of CH4, which is your methane, which is 0.32, plus the percentage of carbon dioxide, that's your percentage of carbon dioxide, which is 0.2 as a decimal. Okay, so that's what we all had. So we can have 0.52. So just make sure, guys, you also work it properly. That's cubic meters carbon dioxide per cubic meter fuel. So just also make sure that you work properly. If there is anything that maybe we make just a mistake on adding and so forth, let me know, guys, because working with calculator, you can make a simple mistake, then it can affect everything. Okay, anyways, that's what we had. And what is the other byproduct? The product, which is the here, we also have water. So that is water. These are the products, and nitrogen is part of it. So the products, you just take them from here and also include nitrogen. So water, how many parts of water from the methane is 2 parts of what? Of water. So that is 2 parts of water. Okay, so it's 2 parts of water out of what? Out of the methane. We take only 2 parts, plus definitely the percentage of what? Of hydrogen. Okay, because it's part of water. So that is 2 times the percentage decimal of what? Of methane. Okay, so the percentage decimal of methane is still the same. This one, 0.32 from here. Okay, so it's 0.32. Percentage hydrogen, which is 0.4. that's 0.40, which is just 0.4. Okay, so that's 0.4 like that. So that is going to give us 1,04. That is cubic meters water per cubic meter fuel. So that's what we are going to have in this case. Okay guys, that's what we had for this particular part. Or you can just like leave it like that, because like okay, let's just have our total. It can make sense, because if I leave it like that, now remember I want to calculate the percentage, so we need also this total. Okay, so let's add our total. In this case, we're going to add the products, which is this one plus this one plus this one. Okay, that's your total, which is 5,176 cubic meters. So this is like the total volume, okay, per what, per the cubic meter of what, of fuel. Remember, we're taking this per the cubic meter of what. So all you need is to add everything properly, just like that. Okay, so that's what you all needed there on this particular question. So it was a continuation. Remember, the first part was the volume of air, then together with the volume of what, the products. So these are the products. Okay, so I think just like this, it's fine. Let's see the other part, which is now to calculate the products combustion expressed as percentages. Okay, the products of combustion now expressed as percentages. So it's simply nothing, guys. You can just take those products as we had, but this time let's just put a small one, guys. Let's just put a small table here, because these are just percentages. Okay, so let's not do as if we are having a lot of things here. No, guys, it's just a simple thing here. So that's our product. So now we need this is 4.24 actually. Okay, so these are your products, then the percentages. Okay, so the percentage, remember the first product is nitrogen. So what you simply need, you take this, okay, the volume of nitrogen over total volume, then times what, 100%. You're talking of nitrogen. Okay, so that's nitrogen. So I'm saying volume of what, of nitrogen over the total volume, okay, times 100%. You have your percentage just like that. So volume of nitrogen is this one, 3.616 over the total volume, this one that you added. Of these three, you just work where you added these three products. Okay, you obtained 5.176 times 100%. Okay, and this is going to give us something like 69. Guys, this is too much. Okay, let us just write it, but it's 69. So you can even write 1 decimal place if you want. Okay, but here I'm just going to use 3 decimal places so that we don't miss each other. But you can use what, 1 decimal place if you want, which means it can be 69,9. Okay, so that is the percentage for what, nitrogen. We move on to the other product. Okay, so we have to move on to the other product. And this thing, guys, it reacts when you are drawing these lines. Okay, anyways, our other product is carbon dioxide. So it's just the same like what we did, volume of what, of carbon dioxide over the total volume times 100%, which is the volume of carbon dioxide here. That is your carbon dioxide here. That's your carbon dioxide, 0.52. So it's 0.52 over 5.176 times 100%. Okay, so you can actually obtain the total now for carbon dioxide, and that's as a percentage is going to be 10 point something like that, 10.046, something like that. Okay, so the degree of accuracy there is not like you have to use 3 decimal place. No, you can even put it 1 decimal place. All what matters is that it must balance at the end, and it must balance. Okay, we move on to the water. So for water, it's still one and the same thing, which is the volume of water here. The volume of water, 1.04 over the total volume 5.176 times 100%. So definitely this must add up to 100%, which is 20,093 like that percent. Okay, so that's what you're going to have. And just like usual, guys, we have to find the total. This one you can just write total, you add everything. So here you obtain 100% if you add properly. That is the percentage that you're going to have, like the total percentage, because it must balance. If you add now, you obtain 30% or another, it means now it's wrong, because it's supposed to give us the exact thing like what we are calculating. So if it doesn't balance now, it becomes a problem. Okay, anyways, that's how you play around these. Actually, you just need to play around the formulas that you're given. And yes, sometimes it's not like you're answering the formula, you're giving the formula as it is. Sometimes it can be you are writing the exact thing, like how the table is supposed to be. And someone cannot even use a table here. Yeah, someone can just do this direct without even a table. So it depends with how you want it to be. Okay, let's move on to another question anyways. All right, on question 5, we are now given a compressor. That is a question on compressors there, where we are given a single cylinder, single acting, reciprocating air compressor. Takes okay, so let's just maybe write down the information that we are given, guys. This is Q5. So actually I'm going to show you like the steps, because this type of a question, it repeats. So I'm just going to show you how you answer this type of a question. Okay, you have your volume here of air per minute. Okay, that is the one that is it is taking in. That is your VE. 2 cubic meters per watt per minute. All right, at that is the inlet pressure, that is P in. Okay, that is P1, P in, which is 102 kilopascal. Okay, air is delivered at, that is your P2. Okay, which is 780 kilopascal delivered at. And the compressor runs at, you are given N, that is the speed of 300 revolutions per minute. Okay, that's 300 revolutions per minute. The free volume is 3% of the stroke volume. That is we are given the clearance volume here versus the stroke volume, VC versus VS, the stroke volume. Okay, so VC is 3%. VC is 3% of VS. Okay, which is 0.03 as a decimal, of which we know that VC is equal to what? V3. These two, the clearance volume is equal to V3, so you can use this in place of V3. Okay, something like that. So what else do we have? The index of compression, which is N. N is equal to 1,3. We are given the index of compression. So the first question is to calculate the stroke volume relating to the clearance. Okay, relating to the what? To the clearance volume, stroke volume, cylinder volume, and the effective volume of air. These must be used. Okay, so these are the steps that you're going to take. Actually, you know that this diagram is something like of this nature. Okay, something of, all right, that's your volume and this is your pressure. So actually you'll be having 1, 2, 3, 4. So the diagram can just help us somehow to just know that P1 here will be equal to P4 and P2 will be equal to P3. Okay, so this is your V3, which is your clearance volume here. This is your V4 and this is your V1. So the difference between these two, that's your VE, that's your effective volume. The difference between these two, that is your stroke volume. Okay, that's what we are having in this case. All right, our stroke volume. So I think everything is there. So let's just work out these. So these are the stages or the steps that you're going to have. Let us start with the given information, the stroke volume, okay, and the V3, which is the clearance volume. Stroke volume is V1 minus V3, okay, that's your Vs from this. So these are the stages that you're going to take, okay. We want to calculate Vs. We do not know this value. So let's start with the first one. We said Vs is equal to V1 minus V3 here. Vs. So what does it mean? V1 minus V3. Okay, this is V3, which is your Vc. Remember I said V1 is equal to V3. So we can write this in terms of Vs. Why? Because we are given Vc. Okay, we wrote it here. We are given Vc in terms of Vs. So connect these two. Vc is equal to what? 0, so that's minus 0,03 Vs. So we want to write this in terms, because we want to calculate Vs. So write Vc in terms of Vs. Okay, so just substitute with Vs, which is like this. So we can make V1 to be the subject. Okay, that's Vs plus 0.03 Vs, which is equal to V1. Okay, so we are writing V1 in terms of what? In terms of Vs. So this is just like 1. So it's 1 plus this 0, so that's V1 is equal to 1 plus 0,3, which is 1,03. Okay, that's 1,03 Vs. So let's just put this aside as if we didn't calculate anything. Let's just put this aside. Let's just leave it aside like that. Okay. I want you to take note from your formula sheet. There is this formula. Now I don't know where did I put this formula sheet, but it's like this. V4 is going to end up like this. V4 is equal to V3 into P4 over P3, okay, to the exponent of 1 minus 1 over n. So this is actually what you're going to have, but in this case we have got our V3, okay. P4, remember we said P4 is same as what? P4 is same as P, this is P2, P1. All right, so this is what you're going to have, P2. So it's actually supposed to be P3 over P4. Okay, P3 over P4. So let's just put it this way, guys. P3 over P4, so that it can actually make sense here. All right, because we need this, because we said P1 is equivalent to P4. All right, that's our P1. Then P3 is P2. So in place of P3, you're going to substitute with P2. So it can be V3, which is Vc. P2 over P1 to the exponent of 1 over n. So that's your V4. Okay, so remember our V4, we said this is the difference here. V4 is there, which is from V1 minus V4, which gives us VE. So we shall talk about this later on, but let us just have this. But everything, make sure it's in terms of what? Of Vs. So how can we write Vc, which is our clearance volume, in terms of the stroke volume? We have to substitute that part that we are given. Okay, it's not here, guys. You see this issue of working with too much papers now. Okay, our Vc here, it's 0.03 Vs into P2 over P1. So that's P2 over P1, these two. Okay, the pressure 780 over 102 to the exponent of 1 over n, our n, which is 1,3. So that's what you're going to have as your V4. So all you need is to simplify this times this bracket. Okay, then Vs, you multiply the answer by Vs. So everything is going to give you something like 0,135 if you multiply this and this. Okay, times what? Times Vs. So this is our V4 in terms of Vs. So as you can see, we have something there. We have V1 in terms of Vs. Okay, here I want you to see something. We have V1 in terms of S, we have V4 in terms of S, but we say that the difference between these two is going to give us VE. So here V1 minus V4 must give us VE. So if that is the case, therefore our VE is going to be V1 minus V4 in terms of S, in terms of VS, which is our stroke volume. So this is going to be like this: V1 here, or V1 minus V4 here. So let's just write it V1 minus V4. So this is V1 in terms of, so that's, you'll see it is going to make sense later on, minus V4. This is your V4 in terms of S. So as you can see, these two can subtract each other because they are in terms of what? VS, which is the stroke volume. So how can we have this? Okay, let's combine these two. If we combine these two, we are going to obtain 0.895. okay, that's what you're going to obtain, which is VS. But VE, we have this. Okay, when we listed our information here, our VE was 2 cubic meter per minute. Okay, 2 cubic meter per minute. So that means we are going to calculate VS by simply dividing by what? By 0.895 both sides. 0.895 both sides. That's our VS. But take note, our VS is going to be what? If we divide by 0.895, it is going to give us something like 2.235 something. But take note, it's cubic meters per minute. This is per minute there, not cubic meters, but it's per minute. So the question is, how am I going to remove this per minute so that I am going to remain with the actual VS? Okay, so that's where we have to use now this information. Remember, we've got revs per minute here. So this is the one that can help us to cancel the per minute that we have. So in order for us to do this, guys, this is per minute means like this, guys. Let me write it this way. It means 2.235 cubic meters like this over a minute. So to cancel this per minute, this rest per minute must be written like this: minute over 300 revs, so that minute and minute can cancel. So that's how you're going to write it as. So it's going to be minute over 300 revs. So 300 revs is just like complete revolution, so it does not affect anything. So the minute and the minute can cancel. That's our VS is going to be 2, our VS is going to be now 2.235 cubic meters over what? Over 300 revs, which is just complete revolution, so it does not affect anything. So if we divide these two, we are going to obtain something like 7.45 times 10 to the power minus 3, which is in what? Cubic meters. So that's your volume, that is the swept volume in this case, of which you can write this as a decimal, something like 0.00745 cubic meters. Is just one and the same thing in this case. Okay, so guys, these are the stages that we had in this case to end up with the stroke volume. So we are related to clearance volume, the stroke volume, the cylinder volume, and the effective volume, which is the last one now, which is this one that we end to relate, and also considering the speed, which is the revs per minute, in order for us to obtain the exact value. That is how you calculate this, just like that, guys. Okay, then we move on to work done. So here, guys, I think it was best for us to have the power, then we can have the work done. I don't know how do you view it, but as for me, that's what is going to be best for me, because I simply have to convert the power to work done. or to convert work done to power. Okay, so the easiest part for me was to calculate power first, which is 5.3. So after power, then I can calculate work done. That is what is easier for me. I don't know for you guys. So I'm going to use this formula for power. I don't know where did I put my formula, but this is the formula. Let me just use this one. It's P1 VE, okay, into N over N minus 1 into our formula sheet. We've got something of this nature, P2. So power machines, guys, is something that is direct because the formulas, you have everything, all the formulas. All you need is to use your formulas perfectly. Okay, so that's your power here, which is given as work done, but this is power. Okay, so P1, that's our pressure, which is, in this case, we are given a pressure of 102. That is our P1, 102. So that's 102 times VE, which is the effective volume of 2 cubic meters per minute. So this is per minute, but power, remember, it must be in kilojoules per second so that it can give us what? Kilowatts. So we must have per second. Okay, so divide by what? By 60. It's now per second because we need per second, kilojoules per second. Okay, times N over N minus 1. This is our N, which is 1,3. So it's 1,3 over 1,3 minus 1. Okay, that's it. Everything into, so you can even put a bracket here if you want, into P2 minus, or P2 over P1. This is P2 over P1. That's 780 over P1, which is 102. Everything to the exponent of N minus 1 over N. So all you need is to substitute this N as it was. So that's 1,3 minus 1 this time over 1,3 minus 1. So make sure that you have to use your calculator properly. This is over 60. All right. So using our calculator, we're going to obtain 9,109 kilowatts. Okay, so this will be our power. Remember, we said this power is kilojoules per second, which gives us what? Kilowatts. Okay, so that is your power in this case. Okay, so now let's get back to the work done now. Okay, let's get back to our work done, which is on 5.2. The work done now, this is how am I going to find it. I'm just going to use this formula. It's easier for me to connect this way. 5.3, because I know that work done, since I have power, okay, I'm going to take my power, which is in kilojoules per second. Okay, to have work done, which is in kilojoules only. Okay, I'm going back here where I have my revs per minute, because I'm given revs per minute, so I have to have this in revs per second. Okay, so this is revs per second. So to remove this per second, I'm going to multiply with second over revs. So I have to convert my N, which is 300 revs per minute. Okay, so that is like this, guys. 300 revs per minute, like this, means 300 over 60. All right, which is something like 5 revs per second. Okay, so this is what you're going to do. It is going to be power, which is kilojoules per second, which is the kilowatt, that the one that you obtain, the kilowatt that is your kilojoule per second, like I explained, which is 9,109. Okay, which is kilojoule per second. So to remove this per second so that you remain with kilojoule only, that is where you have to write second over revs, just like what we did in our previous case. So it's going to be the opposite. So it's going to be second over 5 revs, because it's now revs. So this is second, and second can cancel. So you're going to obtain 9,109 over 5, which is in kilojoules per. These revs is just like complete revolution, so they don't affect anything. That is the good part of it. Okay, so that means we are going to obtain something like 1, if I'm not mistaken here. Right, that is 1,8218, then it can be 22 like this, okay, which is just kilojoules. So that's your work done. So that was like the easiest way that we could have, but it's one and the same thing, guys. I don't know how. Let's see, let's talk, guys, on the comment section. Let me know how was it best for you to attempt this question, and did you actually obtain those values like what we did? Okay, the last part, which is on question number 6, we are given an impulse turbine. Take note, we are working with what? With an impulse turbine. Okay, so we need to know the characteristics of an impulse turbine. Remember, an impulse turbine is actually of this nature. Let me just put it this way. A sketch, maybe it can help us. Something of this nature. They can be longer side than the shorter side. So I'm going to have a sketch of this. Okay, then we can have the actual diagram now. So we are given that it has got a mean blade speed of 300 revs per minute. Okay, so that's 300 revs per minute. Let's write our mean blade velocity, which is your u here. So let's just put it as u, which is 3. This is a sketch, okay, 300 meters per second. Okay, then also take note of the scale, 1 centimeter to represent what? 50 meters per second. So this one you divide 300 divided by 50, okay, which is 6 centimeters. So this is actually 6 centimeters. So I'm putting a sketch, then I'm going to draw it later on. What else are we given? We are given the speed of the turbine wheel is 230 revs per minute. Okay, so we are given n, which is 230 revs per minute. Okay, and the nozzle angle is 20 degrees. Okay, remember, guys, the nozzle angle is the angle that, remember, this nozzle entering, okay, as the steam is entering, which is what? At 20 degrees here. That is our angle of 20 degrees here. So that's 20 degrees somewhere there. And the gas leaves the nozzle at a velocity of 800 meters per second. Okay, so the gas is leaving here. That is your V1. Okay, so let's just put this as V1, which is at what? 800 meters per second. So I'm just going to write this V1, 800 meters per second. And in centimeters, remember our scale, divide by 50. So 800 divided by 50, which is 16 centimeters. Okay, that's 16 centimeters. Okay, and it leaves, that is the mass of what? Of the gas, which is 2 kg. So the mass of gas is 2 kg. It leaves at 2 kg per watt. That is the mass. Okay, I think, yeah, that's the mass per second, because this is meters per second, so it will be 2 kg per second. Okay, then the blade outlet, so angle is 20 degrees. Okay, remember, this is our blade here, the inlet. Okay, so this is the blade inlet, the blade outlet. So this is the outlet here of 20 degrees. Okay, the inlet, this one, that is your blade. Okay, so this is inlet. We are going to talk about this later on, but that's what we have got. And the angle, okay, so the coefficient here of friction is 0.75. That is K. K is equal to 0.75. What is the relationship of K? Remember, K helps us to say if this is our VR1, okay, and this is our VR2. This one will be our VR2. This one is V1 and this one is V2. So actually the relationship is that VR2 is equal to K VR1. Okay, which is the velocity that is it in the inlet to the blade. So that's what you're going to hear. So this is just a sketch. Okay, so not wasting much of your time, guys, let us quickly have a diagram of how it is going to be. So this is supposed to be in a landscape. Take note, construct a velocity diagram in landscape orientation, label all angles and the velocities in meters per second. Use a scale of 1 centimeter to 50 meters per second, the one that we talked about. Okay, so let us just start with this line. It's going to help us to have everything done. Okay, so I'm just going to draw this line. I'm going to use pen so that it can be clear, but you're supposed to use pencil, guys, okay, on your diagrams, and make sure that everything is what is super clear. Okay, so this is just a reference line, so it's not specific where exactly it is going to be at, something like that. Okay, and also, guys, I'm not having like the quality of things to use here. It's just small things, but they can help. Okay, guys, let's just put it this way, because I've tried like to look for these things, and I don't know where actually did I drop these instruments, guys, but this is how actually it was supposed to look like. Okay, I'm just going to explain. Maybe you can understand me from this particular part, but actually what you're going to do is to just rework on this on a separate video. I think that can work so that it can be easier for us. Okay, so I'm just going to do that in our another class. Work this redraw so that you can actually see what is happening, because here it's like something else. Okay, anyways, remember these two, they were direct. These two angles, you're supposed to have your V1, okay, and the angle. And in order for you to have VR2, okay, that's, you have to measure VR1. So in this case, according to my diagram, it was 10.6 centimeters. Then I multiplied by 50, got 530 meters per second. Okay, then to find my VR2, that's where I had to multiply now by K, which is 0.75. So you just multiply direct 0.75 times VR1, which is 530. Okay, that is this value, 397.5. and your VR2, you multiply direct 10.6 centimeters, just multiply direct, which is going to give you 7.95 centimeters, something like that. Okay, then definitely your velocity of flow 1, okay, you measure it, which is 5.47. So I don't know, according to your scale, I mean according to where you are drawing, because sometimes it might not be exact, because remember it's a drawing, so sometimes you remember you'll be given a tolerance of whatever that you'll be doing, but that's how it was going to look like, a little bit like that. Okay, so like I said, I'm going to come back and explain this in a separate class. I think you can understand me much better. Okay, anyways, on 6.21, from the diagram, calculate the blade inlet angle. Okay, so the blade inlet angle was this one, that is the inlet, this one. So you have to measure that angle, that is your theta here. So guys, if we are to measure this properly, now the instruments are not there, but this was giving us something like 32 degrees here. All right, so you measure that angle, and the one that is leaving here is 61 degrees, that's your beta. Okay, so this is 32 degrees. This is our beta here, which is 61. So it's not like your answer is supposed to be within these values. Okay, then the power in kilowatts, that's the last part. So remember, power is taken from what? From the total what? From the total velocity. Between these two velocities, you add these two, we obtain 815 meters per second. That's where you can have your power. So that's 6.23. okay, 6.23. So our power is going to be mass, and this mass, it must be per second, which is the one that we had is already in per second, times the blade velocity, which is u, times VW. So let's just use this VW. Actually, it was supposed to be VW1 minus VW2, which is like a plus, so it's going to add. So that's our mass. Our mass, we had our mass, which was 2 kgs here. So it's 2 times the u, which is 300. Okay, it's not 300 here, so it's 300 times VW, which is this 815. According to my diagram, is 815. So I don't know according to yours what are you having, but mine is 489,000, like that, which is 489 kilowatts. So that would be your power in kilowatts, as it is given in kilowatts. So like I said, guys, I'm going to redo this, work on it, sketching, because now I don't know how did I misplace. There are a lot of things here, and I misplaced all the instruments that I had, the one for measuring. So anyways, what you're going to do, work on separate class. But let me know, guys, on the comment section. Let me know the areas that we can actually work on, the question papers that we can actually work on. But that's what we had, guys, to have a total of 100 marks in this question paper, which was written in July 2022. So I don't know, guys, if we can be able to be preparing for N6 or preparing again for N5 to redo again. So if you are preparing to go further, it's fine. If you are preparing to redo, then it is the right time now to start working on your areas, so that you polish up with the time that you're having. So that's it, guys, for Mason African Motives, working on power machines N5. Till we meet again.